Okay, we're going to continue our discussion on chapter 5, rational power and root functions. Now let P of x and Q of x define polynomials. So we have two polynomials, one we call it P of x, the other one Q of x. For the rational function, f of x equal to P of x over Q of x, written in lowest term and for real numbers a and b. If absolute value of f of x approaches infinity as x goes to a, then the line x is equal to a is vertical asymptote. If f of x goes to b as absolute value of x approaches infinity, then the line y is equal to b is a horizontal asymptote. This all makes more sense as we look at more examples. Let's take a look at find the domain and asymptote of the graph f of x equal to x plus 1 over 2x squared plus 5x minus 3. First thing you want to look at for the vertical asymptote. To find the vertical asymptote, you want to set the denominator equal to 0 and simply solve for x. You have 2x squared plus 5x minus 3. We know how to factor this. This is factorable. That becomes 2x minus 1 times x plus 3. And you solve for this, you get x equal to 1/2, x equal to minus 3. So these are my vertical asymptote. These are the line that my graph gets closer and closer to that. And once again, to find a vertical asymptote, you take whatever polynomial you have at the bottom of the fraction, you let it equal to 0, and just simply solve for x. If this is not factorable, you can use quadratic formula. So the asymptotes are x equal to 1/2 and x equal to -3. Since I know my asymptotes, I can know my domain from -infinity to -3. It's not going to touch -3, and then from -3 to 1/2, the graph is not going to touch 1/2. And then from 1/2 to infinity. Now, horizontal asymptote can be found by dividing each term by x to the power of 2. If I divide each term by x to the power of 2, why x to the power of 2 here? Because if you look at your original equation, we had f of x is equal to x plus 1 over 2x squared plus 5x minus 3. You look at the greatest exponents that you have here because it's x squared. We divide each term by x squared. If this were x cubed, you would divide each term by x cubed. You can reduce x over x squared to 1 over x and 2x squared over x squared, that just give me 2. 5x over x squared give me 5 over x. You reduce all that. As x get larger and larger, 1 over x is going to get smaller and smaller. So if you have 1 over x, as you increase x to infinity, 1 over 10,000 becomes a very small number. As I increase x, then 1 over x would be almost nothing, would be equal to 0. So as I increase x, f of x would be equal to 1 over x becomes 0, 1 over x squared becomes 0, 5 over x and 3 over x squared all becomes equal to 0. So this whole thing would be equal to 0 over 2, which is equal to 0. Therefore, the line y is equal to 2 is your horizontal asymptote. That's how you find your horizontal asymptote. If you all do all this and you get 2 here instead of 0, then y is equal to 2 would be your horizontal asymptote. So remember, for the vertical asymptote, we only look at what we have at the bottom of the fraction. We took this polynomial and let it equal to 0. But for the horizontal asymptote, we're going to use this method here to find the horizontal asymptote. So y is equal to 0 would be your horizontal asymptote. Find the domain and asymptote of this graph. We have 2x plus 1 over x minus 3. Vertical asymptote. Remember, to find the vertical asymptote, we take what we have at the bottom of the fraction, which is x minus 3, let it equal to 0, and solve for x. That would be your vertical asymptote. So x equal to 3 is your vertical asymptote. So we can find the domain would be from -infinity to 3 and from 3 to infinity. Horizontal asymptote. If you divide each term by x, because the highest exponent is x, remember the f of x was 2x plus 1 over x minus 3. The higher exponent in this case is x. Divide each term by x, simplify it as you increase x, make x larger and larger, 1 over x and 3 over x would approaches 0. So f of x would be equal to 2. So as x approaches infinity, the line y is equal to 2 would be your horizontal asymptote. Once again, to find the vertical asymptote, you just take whatever you have at the bottom of the fraction, let it equal to 0. To find the horizontal asymptote, you want to divide each term by the highest exponent you see, and you ask yourself, as x goes to infinity, what's going to happen to the function? In this case, terms to equal to y is equal to 2. As you can see, y is equal to 2 would be this line here, would be your horizontal asymptote. Your graph going to get closer and closer to this line. It never reaches that line. Let's find the domain and asymptote of f of x equal to x squared plus 1 over x minus 2. You set the denominator equal to 0 first. X minus 2 equal to 0, so x equal to 2. Setting the denominator x minus 2 equal to 0, that shows that x is equal to 2 would be your vertical asymptote. So your domain would be from negative infinity to 2, and 2 to infinity. The horizontal asymptote can be found by dividing each term by x squared, and look and see what happens to your function as x approaches infinity. As x gets larger and larger, this term here goes to 0, so as these terms at the bottom of the fraction. So we get 1 over 0. Since 1 over 0 is undefined, then we won't have any horizontal asymptote. And this happens, by the way, you may want to write this in your summary sheet. Whenever the degree of the numerator is greater than the degree of the denominator. So remember we had f of x is equal to x squared plus 1 over x minus 2. So the degree of the numerator is 2, whereas the degree of the denominator is 1. When that happens, then you won't have any horizontal asymptote. However, you have another asymptote that we're going to introduce here. If I divide x minus 2 to x squared plus 1 using the long division, x minus 2 divided by x squared plus 1. Everybody should know how to use long division by now. You would get x plus 2 as a quotient, and the remainder would be equal to 5. I'm going to put 3 dots here. I'll let you work on that long division. But we know the remainder would be equal to 5. So what that means, x squared plus 1 over x minus 2 is equal to your x plus 2, that's your quotient, plus remainder over divisor, 5 over x minus 2. Now, as x approaches infinity, this portion here, remainder over divisor would be very, very small number. Almost nothing. So you would end up having y is equal to x plus 2. So the line y is equal to x plus 2 is asymptote, which we call it oblique asymptote. It means it's neither vertical nor horizontal. It's like a slanted line. Y is equal to x plus 2 is another asymptote. It's not a horizontal asymptote. It's not a vertical asymptote. So as you can see, your graph going to get closer and closer to this y is equal to x plus 2 when you draw that. And we already have found my other asymptote, x is equal to 2. And my graph going to get closer and closer to these two asymptotes. Now, this page pretty much summarized what we talked about so far. I suggest that for those of you watching this later at home, to pause this section and read through these steps for these finding the vertical asymptote, horizontal asymptote, and so on, and take a good note of those, because these are the steps you have to take. If you remember, like when we looked at how to find a vertical asymptote, you look at what you have at the bottom of the fraction, you take that polynomial that's equal to 0 and solve for x. And for horizontal asymptote, we divided each term by the highest exponents, and we looked at as x goes to infinity, what's going to happen to my function. So this page here and this page here, how to find the other asymptote, I'm going to let you pause this page and get all the information on that, because we talked about all this already. And so as this one, how do we get slanted line or oblique asymptote? So these are information you need to kind of go over it to know how to find the asymptote, as we did on those examples. And these would be the steps for finding the x and y intercept and all the asymptotes. And finally, we can get all those information together to graph the line. So these steps should be followed for each example to complete the sketch. All right, let's take a look at some examples now. Here we want to sketch f of x equal to x plus 1 over 2x squared plus 5x minus 3. So by now, I'm assuming everybody looked at all those steps and made a note of that. So now it would be a good time to pause the session and see if you can sketch this using those steps. Now, we did some of this problem previously. You may want to rewind what we did before. We said to take what you have at the bottom of the fraction here equal to 0 and solve for x to find the vertical asymptote. We did this part already. we factored this polynomial at the bottom of the fraction into 2x minus 1 times x plus 3 from the previous example. And we find x is equal to 1/2 or x equal to minus 3. And that's how we find these values here to find the domain. And the vertical asymptote, then x equal to 1/2, x equal to minus 3. Same example we did previously. From the previous example, again, we find the horizontal asymptote. If you recall, we divided each term here by x squared, and then we looked at the function as x goes to infinity, and we found y is equal to 0 was the horizontal asymptote. The y-intercept would be one of the easiest one to find. If you let x equal to 0, solve for y, that would be your y-intercept. If you look at your function, if I let for each x 0, you can see the y-intercept would be minus 1/3. That's an easy calculation. X-intercept, you let y be equal to 0 and solve for x. That requires sometimes factoring or using the quadratic formula. So if I let my y, or x plus 1 over 2x squared plus 5x minus 3 equal to 0. If you cross multiply, so it would be only x plus 1 equal to 0. So x equal to minus 1. So this would be your x-intercept. To find whether your graph intercepts the horizontal asymptote, y is equal to 0, we have to solve for it. You take the f of x, let it equal to 0, and see the solution. The solution to the equation was found in step number 4. The graph intercept is horizontal asymptote at this point. So we do get the intersection there. Step number 6, the x-intercept and the vertical asymptote determine the following open interval of the domain. And basically we can gather all this information. What we can do is you can pick a point in between those regions that you created. So if you look at from negative infinity to negative 3, from negative infinity to negative 3, if I pick a point like minus 4, you can see the value becomes negative. So it means your graph is going to be below x-axis, like that. From negative 3 to negative 2, if I pick a point, let's pick a point like negative 2, you see that value becomes positive. As you can see, my graph would be above the x-axis. And if I pick a point from negative 1 to 1/2, like 0, you can see that whether it would be below or above. And from 1/2 to infinity, if I pick the value like 2, you can see the value would be positive, would be above x-axis. So all these behavior of the graph can be verified by picking a point within these regions. Let's take a look at this other graph. F of x equal to 2x plus 1 over x minus 3. We looked at this before. If you recall, we take x minus 3, let it equal to 0, so x would be equal to 3, and that is my vertical asymptote. From there, we can find the domain. So that's how you find vertical asymptote. You take whatever you have at the bottom of the fraction, let it equal to 0, and solve for x. The horizontal asymptote, we did that before also. We divided each term by x, if you recall. You may want to rewind the session to that example. If you divide each term by x and look at the function as x approaches infinity, and we find y is equal to 2. We did all that. If x equal to 0, that's an easy calculation to find the y-intercept. Y-intercept is minus 1/3. That's my y-intercept. To find the x-intercept, you let y be equal to 0. So you get 2x plus 1 over x minus equal to 0. You solve for x, and that's how you can find your x-intercept. As you can see, the graph doesn't intercept the horizontal, because if I let this equal to 2, it won't have any solution for that. You can verify that here. We have 2x plus 1 over x minus 3. If I let this equal to 2, if I cross multiply, I get 2x plus 1 is equal to 2x minus 6. Obviously, there's no solution here. So that means my graph is not going to intercept that asymptote. And pretty much we put everything together to graph the function. We have our asymptote, where my graph is going to intercept x and y axis, if any. And then these points also would help me to pinpoint the approximate location of my graph. So if I let x equal to 6 and solve for y, I get 13/3. If I let x equal to minus 4, y would be equal to 1. And if x equal to 2, y is equal to minus 5. So these points will help me to see where my graph is located. And from there, we have to show this graph when it passes through these points and get closer and closer to these lines. And that's how we can graph it. Take a look at the graph of 2x squared over x squared minus 1. You notice that in this example, the exponents at the top bottom fraction are the same. Okay, let's see what happens if they're the same. We want to find the domain and the asymptotes. If you recall, we just take whatever you have at the bottom of the fraction, let it equal to 0, and you get two lines here. X equal to plus and minus 1 would be your vertical asymptotes. So now we can find the domain to be from negative infinity to negative 1, negative 1 to 1, 1 to infinity. So the numerator is 2x to the power of 2, and the denominator is x squared minus 1. Both have the degree of 2 with the leading coefficient of 2 and 1. So in this case, the horizontal asymptote would be equal to y is equal to 2. We could use that method that we talked about, divide each term by x squared, and as x approaches infinity, see what's going to happen to y. So in this case, when the degree of the polynomial at the top and bottom fraction are the same, the horizontal asymptote would be the coefficient of the polynomial at the top of the fraction over the coefficient of the polynomial at the bottom fraction. It would be 2 over 1, or just simply 2. So you can make the note here also, there is no oblique asymptote because the degree of the numerator is not exactly 1 greater than the degree of the denominator. Remember, the slanted asymptote appears when you had like x squared over x, or x cubed over x squared. When the degree of the polynomial at the top of the fraction is 1 higher than the degree of the bottom, then that's when we have that slanted oblique asymptote. In this case, we don't have it. We can let x equal to 0 solve for y. That would be your y-intercept, would be 0, 0. And you can find x-intercept the same way. You let f of x equal to 0 solve for x. As you can see, it passes to the origin. Now, we also can find whether the graph intercept the horizontal asymptote y is equal to 2. You just simply let this equal to 2 and see if that happens. Now, if I cross multiply this, you see there's no solution. So it's not going to intercept my asymptote. My graph not going to intercept my asymptote because there's no solution here. And we can find few points in between those regions, as we did in the previous example, to graph or function here. As you can see, my graph getting closer and closer to these three asymptotes. There's no slanted asymptote. We find the x and y intercept to be at 0, 0. And these other points kind of give me the pinpoint the location of the graph. Let's take a look at this other example. We have f of x equal to 3x squared minus 3x minus 6 over another polynomial with the same degree. Both are degree 2 here. In this example here, we want to find the domain and vertical asymptote. So what we do is we just take whatever we have at the bottom of the fraction, set it equal to 0, and that gives you x equal to minus 4. That's factorable. So in this case, since the numerator is not 0, when x equal to minus 4, the only vertical asymptote has equation x equal to minus 4. So now we've got our domain, negative infinity to negative 4, union that with negative 4 to infinity. In this example also, the both numerator and denominator has a degree of 2 with the leading coefficient of 3 and 1. So we said that would be your horizontal asymptote, would be 3 over 1, which is 3. Y-intercept can be found rather easily. Let x equal to 0, solve for y, would be minus 3 over 8. X-intercept, you have to let this equal to 0 and solve for x. This is factorable, so x equal to 2 and x equal to minus 1 would be your x-intercepts. We can set f of x equal to 3 and solve the location of the point where the graph intercepts horizontal asymptote. So in this case, if I let it equal to 0, and you can see in this case, it does intercept the horizontal asymptote at this point. We do have a solution. So the graph intercepts this horizontal asymptote at point negative 2 and 3. This is all the information you need to start graphing our function. And we're going to pick up some points in between those regions to pinpoint the graph to sketch them. So as you can see, the graph gets closer and closer to this asymptote. It does across the horizontal asymptote as we calculated at the exact point minus 2 and 3. And we can see this graph going to get closer and closer to this asymptote. Let's take a look at this one. F of x equal to x squared plus 1 over x minus 2. So we looked at this as a previous example that the vertical asymptote can be found by letting what we have at the bottom of the fraction equal to 0, x minus 2 equal to 0, so x equal to 2. That would be my vertical asymptote. We did that before. And if you recall, we divide x minus 2 into x squared plus 1, and we find the oblique asymptote. We did that calculation already. Y-intercept, you let x equal to 0, solve for y. It has no x-intercept, because if I let this equal to 0, there would be no solution, no real zeros there. And the graph doesn't intercept the oblique asymptote. We can verify that. And that would be my graph. This is my oblique asymptote. And my graph is going to get closer and closer to these asymptotes. And we can verify all these using our graphing calculator. Take a look at this one. F of x equal to x squared minus 4 over x minus 2. We need to simplify our expression. That's our first step. In this case, we can factor what we have at the top of the fraction to x minus 2 times x plus 2. That's the difference of the square. So this whole thing would be equal to x plus 2 if x minus 2 is not equal to 0. In other words, x cannot be equal to 2. If x is equal to 2, then f of x would be equal to x plus 2. So what that means is this is really a linear function, except there's a hole at x is equal to 2. When x is equal to 2, y is equal to 4, your graph is not going to have any parts right at this point. When you use your graphing calculator, it would show the hole there. And keep in mind, the graphing calculator is not going to show the asymptotes. So take a look at this example. We looked at x squared minus 1 over x squared minus x minus 2. Similar problem like this before. In this case, the degrees of the polynomial are exactly the same. In this case, we want to write in the lower term. This is factorable. So if I factor this, you would find that is equal to x minus 1 over x minus 2. We want to make sure that x is not equal to negative 1, because we are reducing that. You can only reduce this when you assume that x plus 1 is not equal to 0. In other words, x is not equal to negative 1. So there's a hole at this point. If x is equal to negative 1, y is equal to 2 over 3. Your graph is not going to pass through this point. So we can find the domain and all the asymptotes we need. Finding y-intercept is pretty simple. We let x equal to 0 solve for y. Let y equal to 0 solve for x. We can find the x and y intercepts. Once again, if you want to find whether your graph intercepts the horizontal asymptote y is equal to 1, we have to solve for them. Let it equal to 1, see if there's going to be any solution. In this case, it's not. It's not going to intercept that. There's no solution there. It's not going to pass that asymptote. And we want to pick some points in between those regions to construct your graph. As you can see, there's a little hole here, as we mentioned. So the graph of 1 over x squared plus 1, if you look at this carefully, f of minus x equal to f of x here, and this would be the graph of this function. There is no x-intercept here. Your graph not going to pass us through x-axis because f of 0 is equal to 1. The y-intercept would be 0, 1. And this function is symmetric with respect to y-axis. We calculated f of x is equal to f of minus x. So that verified that symmetry there. You can use a calculator to verify that. Construct the rational function. So this would be an example that we did earlier. This would be a good one to pause at this point, see if you can come up with all the x-intercept, y-intercept, oblique asymptotes, y and x asymptotes. This was the example where we can divide the long division to find my oblique asymptote, and that would be the graph of function. So for that one, I would suggest you pause the session and go through all the steps like we did before, and also confirm that with your graphing calculator.